Hi, everyone. Sorry for the little bit of a delayed start there. We had some technical difficulties. This is still just our second week doing this, so we're still figuring it out, but I think we got it working. We may have some people joining us throughout as we deal with links and things like that. So this is the second of the new sea ice portion of the IGS Global Seminar Series. And so this week we have Lettie Roach from NASA and Columbia, who's going to be presenting on Antarctic sea ice. And then we have Kent Moore, who's going to be presenting second, and he's going to be talking about sea ice conditions in the Beaufort Sea during summer 2020 and sort of preconditioning of that situation. And of course, Kent is from the University of Toronto here in Canada. My name is David Babb. I'll be chairing it today. My co-chairs are Alec Petty and Petra Heil, who are also on the call here. We're going to split the seminar into two 30-minute periods approximately. So we'll have Lettie give a presentation, work through questions there, use the raise hand function or throw your questions into the chat. We'll wrap up the Antarctic side of things, and then we'll move north to the Arctic, and we'll start with Kent's, and we'll deal with questions then. So yeah, with that, I will let Lettie take it away.
Okay, hopefully that that shows up okay.
Yeah.
Great. Okay, great. Well, thanks very much. Thanks for coming. Yeah, so today I will talk about asymmetry in the seasonal cycle of Antarctic sea ice, and I'll just get right into it. So this figure shows the time series of annual average sea ice extent from a satellite going from 1979 to present. For the Antarctic, this is from the Sea Ice Index. I like to show this because I think it highlights the large interannual variability that we've seen in Antarctic sea ice extent. And then this only goes up to 2020, but in the past year, we've had a recent record sea ice low. If you were to compare this to the equivalent from the Arctic, so the annual mean Arctic sea ice extent shown in the gray, you can see that there's really large interannual variability. So we've got particularly this large dip going into 2016 was a really large swing in, larger than anything that you see in the Arctic record. But in spite of the large interannual variability in Antarctic sea ice extent, the shape of the seasonal cycle is remarkably consistent. So first, it's worth highlighting that this is a really large change. So each year, the Antarctic seasonal sea ice extent area, it grows about sixfold, going from about 3 million kilometers squared to 18. And then, so here I've shown each of the 40 years from the 1979 to 18 record in thin purple lines, and the mean of those is shown as this thick black line. So you can see that even though we've had this large interannual variability, the individual years all show very similar seasonal cycle. And in particular, there's this seasonal asymmetry between a slow advance period as the ice extent advances, as compared with a fast retreat period. And this is something that's been noted since the beginning of satellite observations in the late 70s. And there have been a couple of mechanisms that have been previously proposed to explain this. So the first gets mentioned in the Physics of Climate textbook, where they say in the Antarctic, the warm ocean waters surrounding the Antarctic continent tend to slow down the growth of sea ice in the fall and to speed up the melting of the sea ice in the spring. And this comes from a paper by Arnold Gordon in 1981, who did an energy budget analysis based on observations and basically found that the air-sea heat flux, he argued that this wasn't enough to cause the rapid melt that we see. And so there must be some upwelling of warm, deep water to accelerate the sea ice melt. But since then, other studies have argued that this contribution would be small, as the meltwater would act to stabilize the water column. Another previously proposed mechanism relates to the atmospheric circulation, and this comes from Enomoto and Omura in 1990, and it relates to the semi-annual oscillation of the atmospheric low-pressure circumpolar trough, or CPT. So the idea is that you have westerlies equatorwards of this line and easterlies polewards, and where we have westerlies, the ice will drift, according to Ekman drift north. So there'll be an expansion of the ice edge. And the circulation pattern is such that you have westerlies over a large portion of the ice during the spring. So this should promote northward drift and therefore have enhanced ice melt because of the ice albedo feedback. And this mechanism has been shown to influence the timing of sea ice advance and retreat in the Western Antarctic Peninsula region. But more recently, it was invoked to explain the asymmetry in the total hemispheric Antarctic sea ice extent. So this review paper by Ayres and colleagues in 2019 found that the effect of winds and the ice ocean albedo feedback together work together on an annual basis to create the very regular shape of the seasonal sea ice extent climatology. But in our study, we kind of wanted to revisit this and try to systematically investigate the cause of asymmetry in the seasonal cycle of Antarctic sea ice extent. And this came out earlier this year in Nature Geoscience. My co-authors were Ian Eisenman, Till Wagner, Ed Blanchard Wigglesworth, and Cecilia Bitz. So we focus on the sea ice extent. So here in the black, I'm showing the 1979 to 1998, just a 20-year climatology from NSIDC. And here I have, note that I've moved the x-axis by 6 months to kind of focus on this retreat period. And then the dashed lines in this figure show the annual harmonic fit to this, just to emphasize this short period of ice retreat. And so on average in the climatology, the summer minimum occurs on February 24th, and the winter maximum occurs on September 20th. So if we define the retreat and advance periods simply by the number of days between a maximum and minimum sea ice extent, then we find that the retreat period is 51 days shorter than the ice advance period. And we're going to call this metric delta. So for the observations, we have a delta of 51 days. You can also compute this for each year of a satellite record, and that's shown here. So you can see that the asymmetry is fairly consistent in time. The retreat is always faster than ice advance, although there is some year-to-year swings, and there's no statistically significant trend over the 40-year record. And then we found that the seasonal asymmetry is also very well captured by the CMIP6 models. These are the latest generation of fully coupled climate models that came out beginning sort of in 2019. And the ones I'm showing here are all those that provided daily historical sea ice output over 1979 to 1998. So I have, again, the observations as the blue cross. So they had a delta of 51 days. The individual models are these black circles, and then this one with the error bar shows the multi-model mean. We find a multi-model mean delta of 53 days over the same period. And this was a really big clue for us, because the coupled climate models are notoriously have issues in simulating Antarctic sea ice. So for example, this plot on the right shows the sea ice area averaged over the historical period for 40 CMIP6 models. These are the green lines. And you can see that there's a huge intermodal spread, with some models having less sea ice in the winter than other models do in the summer. And so for the fact that the models were able to capture this measure of asymmetry, that seems like a really remarkable level of agreement given the other issues. We looked further back too, and we found a similar picture in CMIP5. And we also looked all the way back to CMIP3, which comes from the early 2000s. And there it's harder to quantify the asymmetry because they only provide monthly data, not daily data. But if you look at the number of months of sea ice retreat in these models, we find that the models cluster on about 5 months of sea ice retreat, or even 4. And It's worth noting as well that not all of these models in CMIT3 represent the dynamics of sea ice. Some just have ice that melts and grows in place, indicating that there might not be a big dynamic component to this asymmetry. So this implies that the asymmetry occurs due to fundamental physical processes. So next we decided it made sense to investigate the mechanism in an idealized model that includes only the most central processes. So to do that, we turned to the idealized model of sea ice and climate, published by Wagner and Eisenman in Journal of Climate in 2015. And this simulates zonal mean surface temperature and ice thickness as a function of time and latitude. So it's an aquaplanet. It just has the one spatial dimension going from equator to pole. We neglect the heat capacity of the atmosphere. And we model the enthalpy in this model subject to insolation, which is multiplied by albedo. And it does vary. So we have albedo varying for ice-free versus open ocean surfaces. Long wave radiation, which is parameterized as a simple linear function of temperature. Heat transport, which is just a diffusive process. And then there's also a weak ocean heating input term. And then this model also has some simple physics to describe the thermodynamics of sea ice, so that the temperature evolves with the enthalpy in the case of open water, but for melting or freezing ice, it's held fixed at the temperature appropriate for those two states. So we run the model for each time for 100 years. It has 400 grid points, and we run it with in constant climate forcing, so there's no climate change. And we track the spatial evolution of the E=0 isotherm as a proxy for the ice edge. For each experiment configuration, we tune the long wave parameter A so that the modeled annual mean, zonal mean ice edge matches up with observations. So that's just making sure that our annual mean, zonal mean ice edge is about 65 degrees south. And we use the present day values for top of atmosphere insolation appropriate for the southern hemisphere. And we found that with this model, even though it's very simple, this produces an asymmetry that's in close agreement with the observations. So we had delta of 51 days in the observations and a delta of 52 days in the idealized model. And it became quickly clear that this had a lot to do with the insolation. So in the original paper describing this model, and this is based on other energy balance models that have taken a similar approach. They use an idealized function for the insolation, which is perfectly symmetric. So this function here. And in this case, the seasonal cycle of sea ice is more or less symmetric. But when we switch from this forcing to using the true present day values at the top of atmosphere for the insolation, this gives us the black circle here with our delta that agrees or is very close to the observations. And you can see here, this is the seasonal cycle of the ice edge in the two different versions of the insolation. So you can see that this big difference in the seasonal cycle is coming at the timing of the summer minimum, where with the true insolation, that moves our minimum about a month earlier. So to try and really understand what was going on here, we decided to then move even further into reduced complexity. And as a first step, we set up a configuration we called no ice, where we stripped out the impacts of sea ice. So whereas we before had an albedo that would vary with ice and ocean, instead here we replaced it with a constant open water value. And then we also got rid of the thermodynamics that meant that we had different temperature evolution, whether you had, depending on whether you had sea ice or open ocean. And so we find that there is a reduction in the amount of asymmetry. So we now have a delta I of 37 days. suggesting that the sea ice physics was amplifying some of this effect. But there is still a large amount of asymmetry here, 37 days, whereas with the idealized insolation, you do in this case have a perfectly symmetrical seasonal cycle of sea ice. We then went a step further and took out the heat transport term by setting D to 0. So this is our no ice, no diff configuration. And this had a very minimal impact on the sea ice. Our delta reduced from 37 to just 35 days. When we do this, this really simplifies our problem, because rather than having this term that connected a couple of the different latitudes together, now we just have a series of ordinary differential equations at each latitude that aren't coupled to one another. And so this is the form of that ODE here. So now we can look at the seasonal cycle at each latitude individually. And this figure is showing the seasonal asymmetry in the temperature at each latitude. So it's defined in the same way as we defined delta for sea ice. That's just the difference between the periods of warming and the periods of cooling. So for the idealized insolation case, you have a perfectly symmetrical seasonal cycle of temperature at all latitudes. But once you add in the true insolation at the top of the atmosphere, we find that we have this offset with asymmetry in the seasonal cycle of temperature that is quite substantial, and it increases as you move towards the pole. So the blue cross here shows the observed asymmetry in sea ice at the annual mean sea ice location, which is 65 degrees south. And at this location in this model, we have an asymmetry of 34 days at the same spot. So this matches our asymmetry in ice extent. So the fact that the seasonal cycle of temperature is matching the seasonal cycle of ice extent here in our simple model suggests that we can understand the asymmetry in ice extent if we can just understand asymmetry in this very simple equation here. So to look into 65 degrees south, what is it about the true insolation that's having this effect? Well, if you look on the top right panel, this shows the true insolation as the solid line. And then the annual harmonic of that is shown as the yellow dashed line. So you can see that compared to the annual harmonic, the true insolation goes flat during the period of polar night, where the annual harmonic goes negative. And it also has a taller and narrower summer peak. And when we put these two curves into this ODE here and solve for temperature, this is when we obtain our seasonal cycle of temperature being symmetric, obviously for the annual harmonic, and then having this asymmetry of 34 days with this curve of the true insolation. So if you just subtract the annual harmonic from the true insolation, hopefully you can see this clearly, that we have these periods throughout the year where the true insolation has a positive anomaly, for example, from November through January. And this positive anomaly in insolation leads to faster warming during that period. And then similarly, from May through July, we have a period of slower cooling in temperature. And then vice versa, where we have our negative anomalies in August through October, and February through April, we have corresponding impacts on the seasonal cycle of temperature there. So it's really very simple, that the fact that we just have this relatively brief and intense midsummer insolation peak, this is what's causing a relatively rapid summer warming and sea ice retreat, followed by a more gradual winter cooling and sea ice growth. And we made an exaggerated cartoon here to try and sketch out this effect. So basically, we should expect asymmetry in the seasonal cycle of Antarctic sea ice just based simply on the top of atmosphere insolation. So what about the Arctic? Clearly, the insolation is concentrated in the midsummer, and we have polar night in both hemispheres. And so we also looked at applying the Northern Hemisphere insolation to the WB15 model. And there are some small hemispheric differences in the insolation because of our current orbit. But still, based on this model, we find that we should have an ice retreat period that's about 43 days shorter than ice advance period. So the effect is slightly muted in the Arctic, but there's still a large amount of asymmetry in the same direction expected based on this model. But when we look at observations, we find that there is an opposite and smaller asymmetry observed. So this figure shows the sea ice extent in the Arctic from the satellite observations as the solid line, and it's harmonic in the dotted line. And so you can see that it's much closer to symmetry, and the asymmetry is actually in the opposite sense. So here it is the retreat period that's slower than the ice advance period by about 25 days. But it's a little, it's not as clear as of a signal. There's a fair amount of interannual variability, although interestingly, no statistically significant trend over this period, although we have seen a decline in Arctic sea ice. And it does occasionally cross the zero line. And so I think this kind of casts the question in the opposite sense in some ways, whereas previous studies have tried to explain asymmetry in the Antarctic, kind of taking the view that this was the unexpected case. Our results suggest that actually the Antarctic is behaving more like what we should expect based on this very simple picture. And really, it's the Arctic that has a more complex seasonal cycle. And of course, there are many hemispheric differences between the two poles. I'm sure you can think of many different processes that might play a role in the differing seasonal cycle in the Arctic versus the Antarctic. But we did also look at the seasonality in Arctic sea ice in the CMIP6 models. So this is delta I, the left figure I showed previously, but this one shows the same for the Arctic. And if we look at the CMIP6 models, the spread is actually quite a bit larger in the Arctic than the Antarctic. And the models do not agree with the observations. They tend to show a positive or near positive asymmetry, whereas we had our observed delta I of about minus 25 days. And so the fact that the CMIP6 models are struggling to capture this feature suggests that it might be more difficult to explain in the Arctic. So in summary, the mean seasonal cycle of Antarctic sea ice extent is asymmetric, with a retreat about 2 months shorter than ice advance. This is consistent in observations from year to year, and it is captured by comprehensive climate models, despite their other biases in the simulation of Antarctic sea ice. Using a range of idealized climate models, we show that the seasonal cycle of top of atmosphere insolation is the primary driver. And the simple explanation is markedly different from those proposed in previous studies. And that's all I have. So I'm happy to take any questions.
Great, thanks, Lettie. Any questions? We'll give people the option to raise hands or address them in the comment box there. Roger, we'll start with you.
Yeah, thank you. Thanks very much, Lettie. Really thoroughly enjoyed that. Of the different components you were testing to explain the kind of smoothed multi-year curves, did you get a sense of which of them might contribute most substantially to the inter-year variability?
That's a good question. We really focus just on the climatology here, and I don't have a good sense of really what the interannual variations are, except that I would say that I think the atmospheric circulation plays a big role in that. The other kind of simplification we made here is I just looked really at the hemispheric sea ice extent, but we also did some analysis looking at the different sea ice sectors and looking at, you know, kind of like individual longitudes, and you do see definite regional patterns in that. So with the insolation, we're just suggesting something that, you know, it's a kind of first order expectation, I think, of what we think the system should be doing. And then there's a whole host of other processes in the ocean, the atmosphere, that will affect that in different places and in different years.
Yeah, smashing. Thanks. I mean, you know, it's the classic one person's noise is somebody else's problem. So just interested in that, because I mean, we see the positions of the ocean currents moving quite significantly and so on in the kind of seismic oceanography world I look at occasionally. So smashing. Thanks very much. Cheers.
Thank you.
Great. Thanks, Roger. And next we'll go to Dave or Mike Steele.
Thanks. Yeah, I had trouble logging in, so Dave let me log in as him, I guess. So yeah, and so I had trouble logging in, so I didn't see. I only caught the end of your talk, Lettie, but you know, I have several questions. But one of them was, so it's all about top of the atmosphere asymmetry, but what's causing that? Did you answer that, or did I miss it?
Well, it's just that at the poles you don't have a lot of light during winter. It's not a fundamental asymmetry in the insolation. It's just that we have a long period of low or no light in the winter versus a short period of concentrated
and that causes
sunlight.
That
causes a deviation in the seasonal cycle, from being a perfect sinusoid.
Yeah, but okay, I guess I need to look at your paper, because I can understand why the shape is not sinusoidal, but the phase shift, I'm not quite getting that.
So really just that, I mean, so I'm hoping that these...
I missed that, sorry, I missed a lot, so.
Okay. Yeah, so just, and this actually isn't a great, you know, if I'd chosen a latitude further north, it would be a bit more exaggerated. But just for the fact that you have this, so relative to your annual harmonic, which is a perfect sinusoid and goes negative, the true insolation is not. And you have this kind of, it has this peaky, you know, the part where it's you know, it's higher than the annual mean for a shorter period versus where it's lower. Does that make sense?
Well, not yet, but I'll read your paper. But
honestly, it is really very, you know, it's really just that you have this period of the summer is short compared to the winter.
Yeah, and so another question. I mean, I've looked at these the timing of the length of retreat versus advance and all that, and when I was writing my loitering paper, and so you know, I like the subject, and so as an Arctic guy, I have the opposite intuition. I mean, advance should be fast because, you know, the ocean just loses all its heat and it just freezes up, and so the rate of advance can be really fast. You can get vast swaths of territory that just gets cold and ice forms, whereas retreat is, you know, slow and, you know, ponderous, because, you know, you got to like push that ice to the north and it's got to melt. And so, you know, the phase of Arctic retreat and advance makes sense to me, and the Antarctic doesn't make any sense to me.
But I mean, really, so this explanation is not really, you know, it's nothing to do with ice at all. It's really just that it's really just insolation and temperature that I mean, maybe this is helpful here. Just that you have a peak of insolation.
Sorry, Lettie,
in the summer.
We can't see the screen that you're talking to.
Oh. Whoops.
We can still see your screen. It might have just been the other monitor.
Oh. How's that?
Season code.
Oh.
Definitely can't follow that.
I don't know how to make it the right one.
There we go.
There you go. That now disappeared.
Oh, it's there?
It was.
Now it's disappeared.
Okay, but just this like idea of the peakiness that you in the winter you have this. In the winter you don't have sun, and then in the summer you have sun, but it's not for very long. So the response in the seasonal cycle of temperature is that it has this this fast period here when you have sun. Does that make sense?
I'll just say I'll read the paper, but thank you.
Can I just ask quickly on that note? So like with that logic, again, wouldn't you expect that to be a bigger signal for the Arctic, where the polar night
is higher up? Yeah,
is higher up. You know, the ice is where the polar night is, whereas the Antarctic is shielded from that by the fact you have the land.
Yes. I mean, that was also my first thought, but then a lot of where the seasonal, I mean, it's changing as climate change, but where the seasonal changes in the Arctic are happening are actually fairly comparable to the Antarctic latitudes. It's kind of over the same region.
Yeah, that was going to be what I was going to ask. If you could just isolate your analysis to where, like, could you just, yeah, the idea is like not that much changes in the middle, so you could just ignore that, block that out from your analysis, and it's more Southern Ocean.
Right, but you still see this overall, you know, this pattern in the Arctic, but it's also more, it's kind of noisier. There's more difference year to year, and more differences amongst the models too. So I think it's, and I think it really makes, you know, this is a very, very simple explanation, and we're thinking kind of in the zonal mean, and the Arctic has a lot more, you know, a different kind of spatial, I would say.
Yeah.
You've got land, you've got areas of not land.
Yeah, and the land, you know, Ian wrote that nice paper about the land part, where, you know, there's that pause.
The muting, right.
Yeah, it has to get through the straits. That's kind of cool.
Interesting. Well, great. Thanks, Lettie. And I'd encourage everyone to check out the paper. Maybe Lettie can drop the link or the DOI in the top bar there.
Sure.
And with that, we'll move over to Kent.
Okay. Thanks very much for this opportunity. Can you see my screen here?
We can see it, and yeah, looks good.
Okay, good. Yeah, so first of all, I want to acknowledge my co-authors on this paper, Mike Still, Axel Schweiger, Jinlun Zhang, and Christian Ladder from the University of Washington. So this is actually these sorts of images here that kind of motivated this talk. So these are sea ice age anomalies for the summer of 2020 and the summer of 2022. And so just looking at these anomalies, what you can see is that if you focus on the Beaufort, both of these summers had essentially anomalously old ice sitting in the Beaufort. And so we were sort of wanting to understand what was the reason for that. If you look upstream, well, not upstream, but over the region sort of north of the Arctic archipelago, North Greenland, this is known as the last ice area, the area where it has the oldest and thickest ice. And there actually are, if you look upstream of the Beaufort, you can see there's actually some differences in these two summers. So there's some idea that you know, there is, although there's old ice, anomalously old ice in the Beaufort Sea both these summers, there are some differences in this region, kind of upstream of the Beaufort, and so maybe different things are happening in these two summers. So if you look at the Beaufort, and again over the last 40 years or so, there's been this transition. If you go back, let's say, you know, early this is the sea ice age record, the Beaufort was sort of characterized in the summer by having a lot of old ice present, whereas now it's really mostly open water or relatively young ice. So there's been this transition. Other people have written about this, sort of the Beaufort is transitioned from an area which essentially had a lot of multi-year ice to one now where it's there's a lot of open water during the summer. You can see out an ice cover as well. So this is from the NSIDC data set. Again, you've got essentially, you know, a lot of large region of the Beaufort, which is ice covered in the summer, early in the record, and now, of course, it's mostly open water. If you look at ice motion, so this is now, again, I'm plotting sea ice thickness and also ice motion, again, both early part of the record and more recently. This is from biomass. And so you can see, in addition to this change in sort of thickness, one can also see that, in fact, there's been sort of an increase in ice motion, especially in the Beaufort. So we're seeing this transition Beaufort's moved from an area which multi-year ice to one where now mostly first-year ice or open water during the summer, and also there's been this increase in ice motion. So there have been a number of papers that have been written on sort of looking at things happening at Beaufort. So we wrote a paper a couple of years ago where we showed that in 2017, the Beaufort High collapsed. And so there was a reversal in the sense of the circulation that occurred during that winter. Dave Babb and his collaborators talked about how that actually led to changes in seasonal ice cover in the Beaufort. Tom Ballinger and his collaborators showed that, again, another collapse of the Beaufort High occurred in the winter of 2020, although the dynamics were probably different, at least in the atmosphere, from what happened in 2017. And then more recently, Mallet et al. Essentially showed that in the winter of 2020-2021, there was essentially what they called exceptional Arctic sea ice transport. And the important part in their abstract is this part I've highlighted. This atmospheric circulation pattern drove older sea ice from the central Arctic into the lower latitude Beaufort Sea, where it was more vulnerable to melting in the coming warm season. And so they suggested this unusual atmospheric circulation may potentially lead to unusually high summer losses of the Arctic's remaining store of old ice. And so this covers part of the work that I'm going to talk about today. So again, sort of the things I want to cover in this talk are what are the processes that are responsible for this old and thick ice in the Beaufort during these two summers? What's the relationship between the ice in the Beaufort and ice in the last ice area, which is this area up here? And then finally, is there some relationship, getting to the point of Mallet et al., is some relationship between the cool season ice volume transport into the Beaufort and summer melt? So what I'm plotting here are two time series. So again, this I'm focusing on this polygon, this region right here. I'm showing you here, this is again from biomass, the summer ice thickness throughout from 1979 onwards. And this is essentially the ratio of the Beaufort ice volume to the Arctic Ocean ice volume, again from biomass. And so you can essentially interpret these time series in a variety of ways. What we did is we essentially looked at a variety of ways to fit these time series. So we looked at linear fits, we looked at piecewise linear fits, and also step functions. The last two had variable breakpoints. And so if you essentially look at all those various ways to sort of fit this data, what you find is that the fit that minimizes the RMS error is actually a step function change around 2006. So essentially one way to interpret this then is that this is this transition then from this kind of old and thick ice regime to this young, thin ice regime here. And if you look at, you can see there's actually 3 summers in this later part of the record. There's actually 3 summers that sort of are outliers, 2013, 2020, and 2021. That occurs in both of these time series here. And we're going to talk about 2020 and 2021. 2013, we recognized was an issue, but we didn't really look at it very much. And then, of course, afterwards, I think I realized, and maybe my collaborators did as well, is that 2013 was this amazing Beaufort Sea breakout, where again, this just again some IR images showing essentially sea ice in the Beaufort from February through to March, and soon you'll see this dramatic transition where essentially the ice all becomes mobile, and as the sort of here it is here now, essentially all this ice suddenly becomes mobile, breaks out, and moves into the central part of the Beaufort. So that's what happened in 2013. We won't talk about that. We'll focus on the last 2 summers here. So what I'm showing here now is this is looking at the anomalous nature of the winter. So I'm looking at the preceding winter conditions in the Arctic Ocean. This is the winter of 2020. This is the winter of 2021. And again, these are anomalies with respect to this kind of new regime, let's say from 2007 onwards. And so what you can see is that these 2 winters are really remarkably different, okay? In 2020, we had this sort of circulation like this. moving ice from the Beaufort up into the last ice area. And then in 2021, the opposite happened. So there was this change here. And so these two preceding winters had very different circulation anomalies. It was cyclonic in 2020, which was, of course, associated with this Beaufort High collapse that Ballinger et al. Talked about. And then in 2021, we had this more typical anticyclonic circulation, okay? And you can see that there are different patterns to the thickness anomalies in the Beaufort. Of course, in 2020, with this cyclonic circulation, one had thicker ice being piled up against Banks Island, whereas in 2021, of course, the circulation was in the opposite direction, and essentially we're inducting thick ice out of the last ice area down into the central part of the Beaufort Sea. Upstream over the last ice area, again, there are differences. Again, they're related to the sense of the circulation. This is easier seen if I take the difference between these two. And what you can see now, of course, is that we now see the differences in these two winters they're much more striking. So you can see that, in fact, there was essentially thicker ice in the last ice area in 2020 compared to 2021. And again, that's because of essentially the circulation bringing ice up into this region. And if you look in the Beaufort, one can see this dipole here. So again, there's thicker ice here and thinner ice here. There's also an interesting dipole around Wrangel Island. And of course, this is just because in one winter, the ice was moving in one direction. So one had an anomaly on one side, a thickness anomaly. In the other case, it was reversed. One sees this dipole shown up here quite nicely. There's also other dipoles, which unfortunately are outside of the region that I'm showing you here. So there are these, although both winters had essentially old and thick ice, the dynamics in the two winters was really quite different. So I want to kind of characterize that a bit better. So this is looking, again, this is winter ice motion and thickness. And so what I'm going to look at is I'm going to look at the net ice area flux through the Beaufort region here. And that's really taking the ice area flux that enters the region and looking at the ice area flux that leaves the region. So I'm going to look at the difference between the ice entering along the northern boundary and ice leaving along the western boundary. So what I'm showing you here is the black curve is the climatology, again, based on the kind of recent period. The shading is 1 standard deviation above or below that climatology. The blue line is 2020, 2021, and the red line is 2019, 2020. So what you can see is the climatology shows, again, throughout the whole winter, these are, of course, cumulative fluxes. There essentially is ice leaving the Beaufort. That's, I think, been quite well shown. But there is a fair degree of interannual variability, but it's typically negative. One rarely sees end of winter ice transported into the Beaufort. And then, of course, we had, if you looked at 2019, 2020, you can see that through that whole winter, we had this positive flux. So we were essentially fluxing ice into the Beaufort from the last ice area. And essentially, by midwinter, it was above 1 standard deviation. So it was, if you like, sort of an extreme event in some sense. If you look at 2020, 2021, it was a little bit different. Essentially, there was some transport in the early part of the winter. This is what Mallet et al. Talked about. But if you look at over the whole season, that was a relatively short-lived event. And then essentially it collapsed, if you like, back to sort of climatology. So although there was some exceptional transport early in the winter, that this whole cool season was closer to climatology. So there was quite a distinct difference, if you like, in the cumulative ice area fluxes in these two seasons. Now I want to jump and look at, can we essentially do some predictability here? So what I'm showing you here is a scatter plot of the, again, cumulative cool season ice volume transport into the Beaufort Sea. That's that, if you like, end result of that last figure. And this is the June 1st ice volume anomaly. I'm showing results both for the, if you like, the old thick regime and the thin young regime. And although the sort of, if you like, the fit is quite similar, the amount of variance explained is actually quite a bit different. So in the old regime, about 15% of the variance in ice volume anomaly can be explained by the cool season ice volume transport, whereas the new regime is closer to 50%. So there's more scatter, if you like, in the old regime, and there's less scatter in this new regime. And that's sort of consistent with the idea in this new ice regime, transport's playing a bigger role. If you now try to sort of go through and predict what happens at the end of the summer, here I'm showing you essentially June 1st ice volume anomaly and September monthly mean ice concentration. And again, the fits are quite similar, but in this case here, the amount of variance explained is about the same. So what this really means is that really, although the transport in the cool season plays a role, the summer, if you like, end of summer ice concentration is really driven by the thermodynamics, what's happening during the summer. So just to conclude then, around 2006, there was this transition from a regime in the Beaufort Sea that was dominated by old and thick ice to one which is characterized by young, thin ice. These summers had interesting mixes of both old and thin ice. But if you look back and looked at the antecedent cool season, you see those very, very different. So 2019-2020 had this anomalous cyclonic circulation associated with the collapse of the Beaufort High. And then 2020-2021 was closer to the climatological conditions with enhanced transport from the last ice area to the north into the Beaufort Sea. So this work was published just recently in Nature Communications, Earth and Environment, and I'll put the DOI in the chat. And although I didn't get a chance to talk about it, one of the things that motivated this is understanding the impact on some of the higher trophic levels, and so of course polar bears play a role. And this is a picture of a polar bear on some old ice, not from the Beaufort, but from the Wandle Sea. But that was one of the things we eventually want to talk about, is how these changes in ice transport are affecting the higher trophic levels. So thank you very much, and I'm happy to answer any questions.
Great, thanks very much, Kent. Anyone with a question? I see Alec has his hand up.
Happy to let anyone else go, but well, I think I'm the first one. Yeah, you talk about transport. Just wondering if you have an idea from your analysis or your intuition how much this is all just purely atmospherically driven, and how much changing sea ice conditions are contributing to any of the variability you're seeing.
That's a really good question. So at least our analysis is mostly looking at the atmosphere as being the driver. So of course, there is a feedback there. If the ice is getting thinner, then clearly, for a given wind, you can move more ice around. So there probably is a feedback there, but we haven't sort of been able to look at that yet. So it's mostly the atmosphere driving things.
Yeah, I was looking at your plots, and yeah, I was just wondering if there's a point in which the thicker ice gets so thin that there's no kind of buffer there, so there could be, very strong advection that maybe we haven't seen before. That'd be interesting to see.
That's one thing that, so one of the follow-ons we want to do is actually try to characterize that, because I think it's an important point to see if we are, seeing those sorts of changes. So that's something we sort of want to do moving forward.
Cool. Thanks.
Interesting. Anyone else? No one else? All right. I've seen the paper, so I've had all my questions answered before. Yeah, great. Well, thanks so much, Kent. And yeah, the link is shared there. And thanks again to Lettie for volunteering to present this week. We really, really appreciate it. Before we wrap up, I'm supposed to plug next week. We have a series of talks coming on. There's 3 talks from 3 different early career scientists. It's a bit more of a glaciology focus. The middle one looks like it has much broader interest. So if you're interested in any of these, please make a point of tuning in next week or follow up with the videos that are again posted on YouTube. The next sea ice talks are taking place at the end of November. It's escaping me right now, but it's the last Wednesday of November. And we have Vishnu Nandan from the University of Manitoba presenting on radar remote sensing of sea ice and specifically how snow complicates that. And we have Will Hobbs from Tasmania giving an overview of Antarctic sea ice conditions. So actually maybe a nice tie-on to what Lettie presented today. With that, we'll wrap it up, and I'd like to thank everyone for joining us this week. And please, as this series starts, make sure to tell your sea ice colleagues about this and invite them to join us for the talks. So thank you very much.
Thank you. Thanks for organizing.
Thanks, guys. Yeah, and sorry for the Zoom difficulties. I struggled too, so we need to find a better way of getting everyone access.
Yeah, we'll work on that.
Thanks. Thanks, Dave.
Thank you. Bye.